I was about like 2:30 woke up at like 5:35.
All right. Hey everybody. So sorry for the delay, and thank you for those who announced to meet as groups. Was that useful to get in groups for a little bit?
Yeah, I guess start.
Okay, great. And for those online, I do apologize. I actually logged into my Moodle while like sitting in traffic, trying to like send an email to everybody so you know what was going on. Gave myself 30 minutes for a 25-minute commute, and then on my way it turned into a 45-minute commute or so. So sorry for that, but thank you for adapting for those of you who are here. So today I wanted to talk about wastewater stabilization lagoons. I think my plan is at this point to kind of send out some practice problems over probably over the next week to kind of start getting you a feel for what types of problems would be on the exam. But for the most part, you can kind of focus on taking care of your senior design for those of you who are going next week, and the papers, the presentations, all of that. And I will announce a schedule for the presentations at some point next week as well, so you can kind of start gauging your timeline accordingly. All right, and so by now I think you should have submitted your next draft. I'll try to get that back to you, I guess, within about a week and a half. Some more feedback for you. So thank you for that. Any questions on logistics or anything before we hop into the lecture? All right, yes?
Do we have to notify you for doing the work, like the senior design?
No, I think I just assume that a fair bit of you will be gone. So like I said, I'm not going to collect attendance during that time, but I'm expecting you to review the material so that you have some knowledge about it. Okay. All right, anything else? Okay, so wastewater stabilization lagoons, essentially what we're going to do is use some sort of a pond to treat wastewater, is the simple way to say that. They are a little bit more complicated. There's a little more that goes on in terms of designing this said pond, but one of the things that kind of strikes you is like, well, wow, we can just use a pond? Like, what? That seems pretty easy. How does that work? A few notes here, just on the kind of the general sense. Some of the advantages are kind of obvious. It's simple, right? If you set up a wastewater stabilization lagoon, it's kind of one of the fancy terms. There's a few terms we'll see and we'll see other people use. But essentially, you've got very low energy costs, in part because you're using nature to do all the energy work. You're getting sunlight to feed the algae, which are going to produce oxygen for you, and you're using wind to aerate the water as well. So you're getting biological activity driven by oxygen from algae, which is biological activity in itself, and by wind and mixing. So temperature is going to be an issue there, but we'll talk about all that. So low energy in terms of what a wastewater treatment company or operation has to put in. Also means, the simplicity gives you a case where you really don't need full-time staff, typically. There are some maintenance things that you need to consider. We'll get to that, but basically you don't want animals getting in there messing up a liner or burrowing through a clay liner or whatever the case may be. You might have some pest control. You want to make sure that there's some control of whatever grass or plants you have growing next to it, again, partly to control the animals. But that's not like a 8-hour or 24/7 every day kind of a thing. They're good for tropical and subtropical regions in particular because you've got lots of access to light, and light is giving us a lot of the energy required for our biological processes. And it's good for cases where you have clay soils where you can't really do a septic field, right? So the septic field, you require soil that can absorb that water and essentially have that absorption field that's going to disperse the water, and clays are going to be not permeable enough, so this is actually a pretty good option if you have a clay soil kind of area. Well, instead of doing that, maybe you can make a pit and make use of the clay because it's going to be impermeable, because that's one of the issues. The disadvantage then would be large land area requirement. So if you're going to treat a lot of wastewater in particular, you're going to use a lot of land. So if land is scarce, that's probably not a good option. But rural areas may well be a good option. I already mentioned the need for some impermeable barrier, because you don't want your wastewater to get into the groundwater or to escape before it has undergone enough treatment. You also don't want infiltration, a lot like when we were talking about the artificial wetlands. We don't want infiltration to cause more water than we were expecting or trying to treat. Now, if you do have a pond that's lined nicely and then you get a big rainfall event, chances are that it could flood, right? And so that's decidedly a problem for a wastewater treatment lagoon, and you can imagine how nasty that would be to be anywhere near that near that area. We already have that issue occasionally when we have cases where we have combined sewer systems where the rainwater goes in with our sewer system, and we try to avoid that at all costs for obvious reasons. Given that these systems are great for kind of tropical climates, while the inverse is kind of true for cold climates, it's not such a great option. In fact, I visited one facility while I lived in Michigan for a couple of years, and it had a wastewater stabilization lagoon, or two rather, and it was really quite amusing because essentially in the winter months, everything freezes in Michigan. It's like the ground freezes, you have to kind of stop construction. So Michigan has like 2 seasons, or maybe 3. It's like winter, still winter, and construction. So when the ground is not frozen, they just do all sorts of road construction everywhere because that's the time they have, right? So they compact all their construction jobs accordingly. And if you think about it in terms of a wastewater treatment plant, particularly a wastewater stabilization lagoon, there's only certain months that it's not going to be frozen because they're not going to heat it, because that would just take a lot of energy. So it just literally, the pond freezes and waste just is added on top and freezes. And so there's certain months where they are capable of discharging, and so then their operation is quite interesting with a buffer in order to allow waste accumulation and then enough time for treatment once things warm up in order for then their discharge can be operated properly. So very interesting, tricky situations there. But that is to show that it is actually possible, just maybe it takes a little bit more care, at least in terms of the regulation of how to make sure it's going to work properly. So not ideal, but maybe possible. Okay, microbe populations are maybe a little extra vulnerable to different shock events in a case like this, since you don't have such, like in a mechanically mixed situation, or like you're an aerated system, you pretty much are guaranteeing the microbes that you want are going to be in very high concentration, right? And you've got a very consistent control of that because you're providing that aeration. So in a case where we have just a pond, if you have a hurricane that comes through, blows a whole bunch of water out, adds a whole lot of water in, or whatever, something like that could shock the system, where you have suddenly a whole bunch of mixing, and your system then, or a large pH change, something can happen where your microbial ecology is disrupted, and it may take a little while before things settle back. The good thing is it should settle back pretty much on its own. As we'll see, most treatment lagoons have a kind of a pattern, so to speak, that develops naturally. So it's somewhat vulnerable, not a terrible thing, but it certainly you could have cases where you have poor treatment for a week or something, right? So it's like there's some concern there, and to add to that, when it is malfunctioning in that manner, typically you're going to have anaerobic processes start to dominate, and then you have hydrogen sulfide being released, which is the very smelly, like rotten egg smell gas. Okay, picture. So, a couple things about the anaerobic ponds then, or these stabilization lagoons. And again, we're coming back to this picture in Mandeville with a little bit more info this time. So there's a few different types of lagoons we might operate, and oftentimes a treatment plant will include more than one in the same setup. So in this case, we have, well, let me just say, the three would be anaerobic ponds, facultative ponds, and aerated lagoons. I think there's maybe a fourth classification just for kind of a polishing step that you might use for maybe phosphorus removal or something like that. But in terms of like the primary treatment tasks, we would have these three. So an anaerobic pond would be, as it sounds, a pond that is kept rather anaerobic. That means you're probably going to have a deeper system, possibly covered. If you do cover it with some material, maybe you can collect methane gas from that. That is possible. And so, but the fact that it's deep is going to mean that most of the water column is shielded from light, just simply because it's so cloudy, mucky, dirty. The light's not going to go very far in. And so then the bulk of that is going to be oxygen deprived, because all the biological activity is just consuming whatever they can. And there's just so much biological oxygen demand that the whole column remains anoxic, or nearly so. It's going to be a small layer at the top. And it's also going to mean that there's not a whole lot of mixing, because if you have a deep channel and the only thing that could provide mixing is a bit of wind and very, very slow flow, you're not going to have that mixing effect where you have in a shallower pond like the facultative. And just a quick note about the anaerobic ponds. They're often used if you have a really high strength wastewater, and they can remove about 80% of BOD, which is not great if you think about it as like a standalone step. But if it's capable of treating a lot of waste, or a really high strength waste, and you're getting 80%, and then you follow it with something that gets a larger percent of the remaining BOD, the remaining waste products, that's actually a pretty good setup. So sometimes you'll have maybe an anaerobic system, which is possibly these ponds. I think these are probably just going straight into the facultative, and then these are kind of after that. But one way or the other, you could sequence like that and have your anaerobic and then a facultative to really have a pretty good treatment train. It's the facultative then, it's kind of our most common, sort of what we're referring to, or what we would kind of default to in a sense, unless we're trying to be a little bit fancy. So a facultative pond then is a medium to low organic loading is what they can handle. They're typically at most 8 feet deep, and then of course you're going to have sedimentation and an accumulation of layer on top of that. So realistically, you might be thinking like 6 feet or something of water, depending on how long it's been in operation, since any kind of a sludge removal. And the surface then is kept aerobic, or the design is to keep it aerobic, because you don't want that hydrogen sulfide gas emitting and sinking up the place, and it's just gross that way. You also want that aerobic process, right? It's not just the odor, but the decomposition of waste. We get better organic oxidation when there's oxidative conditions, right? So we're turning more of the stuff to CO2, and it turns out that we'll see algae is also taking that CO2, and that's a useful synergy there. So that gives us pretty high BOD removal, and normally those are, that would just be a system where you're using wind to provide the mixing. If you want to get a bit fancier, you can do an aerated system, so an aerated lagoons, that would be these guys. So it's very likely, in my view, that these two are just facultative, and then we have these three, or I guess 2.5 maybe, which are essentially aerated, which provides the kind of similar conditions. Facultative, it's kind of referring to what kind of bacteria can grow. And so there's an oxygen supply, and in this case, what we're talking about is some sort of mechanical addition of aeration, right? So in this case, we have a fountain, or lots of fountains, it looks like. You could have a mixer that's just providing mixing, and that's going to help with aeration. So you might have a paddle wheel system where you're kicking up water into the air and inducing a bit of a flow or something, and that would provide the aeration as well. So you're adding it in some way. You might call it purely aerobic, if you've got enough energy added, so to keep the whole water supply aerobic, or you might call it aerobic anaerobic, meaning like a facultative pond, you have a layer that's anaerobic kind of on the beneath the top area. Okay, so that might look something like this, where you have some bit of pre-treatment coming into your wastewater treatment. Usually that's just going to be a grit chamber, kind of like what we saw in the artificial wetlands. I was showing the place in France where we had a kind of a grit chamber that was collecting all the garbage that ended up in the water before having the waste flow into the treatment system. So something kind of very generic, very simple like that as a pre-treatment step. Certainly you could think of some very low-tech solutions for that. Then you would send the water into facultative ponds, so that would be in our picture up there. Have those mixed, and then into something that's a little bit more of a plug flow reactor style pond after that, just to give it a bit more time. And if you think about these as treatment operations, you pretty much are guaranteed sedimentation along the way, right? And continuous sedimentation. So you've got, if you've got the like mechanical mixing added, then of course you're not really gonna have sedimentation there. And so that would be a good reason to then have a calmer period, or even secondary, tertiary lagoons to continue that sedimentation, continue whatever biological processes are going to happen. It may also be the case that this is just a backup, where they can divert flow from one to the other in case they need to do some maintenance on one of them. So that it could just be their capacity is rated such that if they had to go full capacity, they'll use both. If they need to do maintenance on one during normal flow, they'll just go to one and not the other. There's another lagoon system we can kind of take a look at. This is a little bit west of Lafayette. And we can see that there's this treatment plant here. And we have a couple of these smaller lagoons. And if we go to Google Earth or Google Maps today, and we look over it, you can actually see there's like some cover put on it. So one of these, if not two of these, are anaerobic intentionally. So they've covered it, shielding it from light. That means we're not going to have photosynthesis happening. We're not going to have mixing with the air happening, and they may even be harvesting some methane. So some of these would be anaerobic, and then aerobic, and you can see there's residential areas right along the way. So I hope they have pretty good odor control for the for those ponds. And then it would go into here, I believe. So it's the flow is probably going into here, perhaps, and then maybe something like that to here, something like that. And then this last pond, you'll have a flow that is a bit of a plug flow. It doesn't matter too much, but it certainly gives you plenty of sedimentation for that process. Yeah.
I lived about 5 minutes away from that, and I didn't know that was a pond. That was for wastewater, so they
Excellent.
control the smell pretty well.
Great. That's neat. Oh, could you see it? Like, were you ever walk around that area? Like,
I mean, you could see it from the road, but I've never walked around it.
okay. And so, yes, if you do come up to one of these, like off a road or something, a lot of times it'll look like, typically here we'll have it fenced in. Some places don't. Like, if you're adding something in a developing country, that would be something to consider. The cost of fencing, it's not super cheap, but it might be worth it because you don't want people getting in. It would be certainly a hazard if they didn't know what was going on. Like, even here we don't, like, oh, it's just a fenced in body of water of some sort. Like, what's that about, right? And then you'll have probably a fairly, or at least reasonably well kept lawn, so to speak, on the berm, and then it's just this exact defined pond system. You're like, what's that? Yeah.
Whenever you say like well kept line, like, is it intentionally well kept, or like, are there any like plants you can put around it to just kind of help with like general treatment?
Yeah. So the plants are like, and the reason to have some maintenance there are really to prevent or to discourage rodents and things. So if you had like lots of weeds growing, you're inevitably going to have all sorts of wildlife coming in there and messing around. And what you don't want is them to then burrow through your liner. Maybe if you have a low flow season, then you get holes in the liner or something like that, right? So you're trying to keep it easy to see if there's a problem and
Obvious
just
that it's
prevent
doing
it.
business.
Yeah, and prevent any sort of rodents or like even rabbits or something that might burrow could be a problem, right? So that's sort of the one of the maintenance items that are typical there. Yeah.
What about like other little critters like frogs and turtles and stuff today?
That's a good question. So
Mess up this whole thing?
in looking over some materials today, I didn't really see much about frogs and turtles. I think I would say frogs are probably going to be unlikely because frogs are usually pretty sensitive to environmental conditions. So I would guess that they would not thrive in the area, but it's certainly the case that you could have some species of fish or something that may be able to be there. I'm not sure what all would, maybe turtles maybe, but I don't know if they. I guess if they tried nesting, that would be a problem. They tend to dig.
Yeah, I used to work in a sewer district, and like there were turtles in like the overflows that we would have because Louisville had a lot of overflows from their combined sewer system, and so like for the areas with the overflow, like I found like turtle shells, like whenever we visited to make sure everything was intact. So yes, they can survive. Although one did die, so I did find like just a shell. So.
Okay, so turtles, yes. Alligators, maybe. Insects, yeah, nutria. So, and I think turtles, maybe they would not be ferocious enough in their burrowing tendencies, nesting tendencies. Maybe snapping turtles would be a problem. I don't know. It's an interesting question. And if you take this to somewhere in Africa, let's say, you got to start thinking like, I don't even know what kind of animals might be a problem here, right? So you really would have to have that like communicate with whoever's operating it. Like, well, here's the problems. Here's why we care. So like if there's something that might mess this up, like let's try to manage that. Insects can be a problem, at least in terms of potential vectors of pathogens or whatever. I don't think that, and there's maybe some standard advice or standard procedures to help control insects, but I don't think there's anything that's like prevent everything, and I don't think it's like a major operational problem either, from what I've seen. Okay, so again, back to the question of why does it actually work? There's that common catchphrase biomimicry. Well, in a sense, we're doing some imitation of natural systems. And it turns out that if you discharge a bunch of wastewater into a natural system, it treats it eventually just based on biological processes. We just don't want it to be consuming all the oxygen in our nature system. So we want to do that in a separate pond before discharging it into what we deem as natural waters. So even in our regulations in terms of how we structure our EPA permits to discharge wastewater, specifically, they say, okay, all waters of the state need to be protected, but we don't count wastewater stabilization lagoons as waters of the state. And I mentioned, I think last time, agriculture ditches, right? There's a couple of exceptions. Ponds dedicated to wastewater treatment are one of them. Because if you think about it, it's like you made a pond, and now we have to protect that pond. Would normally be the case. Got a question?
Yeah. Was there like a case that like made that the case? Was there like a notable?
There might be a
like,
court case of some
lawsuit?
sort. There probably is.
Or was that written in? Or I guess written in like the 90s amendments?
That is a good question. I bet we can find that pretty easily. If we have time at the end, I'm going to pull up the permit writer's manual that I have just to see. We'll try to answer that in a little bit.
Yeah, no worries.
Okay, that's a good question. So maybe there's some funny lawsuit that drove that distinction. Okay, so how it works then, I already mentioned, but it's nice to have a good diagram here. really the sunlight is driving a lot of our work, our energy, and wind. So we've got oxygen production during the day. So during sunlight hours, and of course if you try to make one of these in Alaska, there's several months where not only are you frozen, but you're also having like almost no sunlight, right? So there's additional challenges there if you were to go in a very northern or very southern location if you're talking southern hemisphere. So we've got CO2 exchange in the water, we've got oxygen exchange into the water, and really these are equilibrium reactions, right? So physically, if we were saturated with oxygen, we would be expelling oxygen based on the saturation points, which could actually potentially happen if you have enough algae processing. And likewise, the CO2 is going to be doing gas exchange as well. So we've got the surface physical phenomenon. These are going to be driven in a large part by wind. And then we've got the biological activity where we have the CO2 and the oxygen being used in different spots. And in a region where the sunlight can penetrate. So if the sunlight kind of starts fading and is not very bright by this point, because there's so many cells, so much biology, it's going to be kind of murky water. You're only going to get sunlight to go so far before it's attenuated. So you have some region or realm there where you've got what we would call facultative. So we've got this aerobic zone, then we hit the facultative zone. I guess actually let me be a little more clear. This says facultative region is including both. But maybe this transition between anaerobic and aerobic is this facultative zone in particular. Okay, I see, that says facultative lagoon. Have a hard time reading sideways. So the lagoon as a whole will incorporate this aerobic zone, facultative zone, anaerobic zone. So we have lots of oxygen here, a little bit of oxygen here, and then no oxygen down here. Okay, so essentially algae are providing a big source of our oxygen here, and the microbes, the bacteria that are not algae, are going to be providing the algae with a lot of CO2, because they're going to be munching on the wastes, consuming wastes, and releasing CO2 from respiration, decomposition, all that. And so essentially what ends up happening is we get kind of a feedback system there, and then in the sludge blanket and in kind of maybe the water just above that, where we're really not getting mixing, it's really stagnant and gross in a way, we're actually getting a lot of anaerobic processes happening, also releasing nutrients and digesting the sludge, which again, if we think back on what we've learned about septic systems and the like, that's actually a really nice thing, because that's going to do a good job removing solids. If you just had aerobic systems, you end up producing a lot of solids, and you're going to have to deal with that pretty routinely. So it's actually kind of a neat way where, again, there's a low-cost element here where the sludge digestion is happening while you're also getting the benefits from the aeration or the aerobic treatment. Okay, another way to look at it, a little bit simpler, from a different book I found that was pretty helpful on this stuff. Essentially, you've got the sludge that's dissolving the stuff, degrading it, digesting it, so you get soluble organics. You also have the wastewater itself adding soluble organics. You've got the bacteria decomposing stuff that's producing lots of nutrients, and the algae are really happy to have those nutrients. Now, the bacteria will also be using some nutrients. They're munching on all this stuff, releasing some nutrients, and then also consuming a bit. But the algae really like to have that access to nutrients, plus all the sunlight. So they're going to produce oxygen then, which is going to provide that for the bacteria. Okay, so this bacterial algal symbiosis, can think of symbioses like sharks and remoras, where one's cleaning one and the other is not eating the other and providing some food scraps or whatever. They're happy to survive that way and thrive together because they are providing great benefits, right? Just kind of the written version of what I've just been saying. So if you look at the typical I guess, chemical formula type of equation, the average chemical reaction that we have that occurs when we've got photosynthesis. We are consuming CO2, we've got water and nutrients. Here we're showing ammonium. Now, you'd probably also have trace amounts of phosphate in some form and whatnot, but it would be on a much smaller scale so that we're not, this is a simplified reaction. To form essentially algal mass, oxygen, releasing some water, and a bit of acidity. So when we have the photosynthesis occurring, we can drive the acidity, the pH downward. We're also releasing some energy here that's kind of referring to the energy used for algal growth, right? So that's kind of algae are gaining energy from this process, from the light and all that. Okay, so I wanted to kind of show you this little figure over here. It's way too small, so we're going to break it into a few parts, but it's kind of a neat figure because what it's showing is this algae bacteria action over the course of 24 hours for 3 different cases, and it's kind of showing like what happens if you have extreme algae growth, what happens if you have kind of normal, and so just a snippet from this book that I was using. Happy to share that if anybody's interested. This is not our book itself. I have a few slides from that, but this is a little bit more technical one. So photosynthetic activity in the stabilization pond demands large amounts of CO2 for algae synthesis. So we need a lot of CO2 for the algae themselves, because obviously photosynthesis, they're taking in CO2. It's another thing I didn't mention, but the bacteria, when they're decomposing stuff, they're producing a lot of CO2. So that's, again, feeding the algae, which feed the bacteria. Okay, so then essentially there's 3 sources of CO2 that the algae synthesis can use, and one would be the CO2 as an end product of fermenting the organics in the pond, so just the bacteria doing their business. CO2 from the atmosphere, so again, the aspect of mixing and temperature is going to affect CO2 solubility. And then CO2 in the kind of inorganic carbon species, so carbonate, bicarbonate, all that. So those 3 sources are what algae can use. And so then this figure, which we're going to take chunk by chunk, is going to be kind of showing that if you have vigorous photosynthetic activity, you could potentially deplete your CO2, and that has some consequences in terms of what's happening with the pH. That would then cause a rise in pH in the pond, because then photosynthesis kind of stops, right? They're photosynthesizing, which is dropping the pH a little bit. And if you take out all the CO2, which is an acid, and you stop producing a little bit of acid, the pH can then climb quite high. Okay, so the first panel here, what we're looking at is on the bottom, this is CO2 in water, so dissolved in water, and we see we've got some amount, I think that's millimoles per liter, 10 to the minus 2. Although I'm a little confused because that should be a capital M. And then we're taking a look at the pH. So during a 24-hour cycle, it looks to me like maybe this is probably midnight. So this would be probably 0 in a 24-hour cycle scale in that manner. So while it's still dark, pH is dropping a little bit. CO2 is increasing because the biological activity happening. There's no or little photosynthesis yet, so there's nothing really consuming the CO2. We're just producing it. Even algae cells, by the way, will go through standard respiration like a bacteria will at nighttime. So if they don't have sunlight, they're going to default to respiration rather than photosynthesis. So all of that's going to be increasing the CO2, and then they start producing CO2, and this will start dropping the CO2 they're consuming, start doing photosynthesis sometime around 6 or 7 a.m. when the sun starts rising and becoming an important source. And that's going to continue for some time, and we'll see the pH ends up rising a bit. We're consuming some of the CO2. So if we're consuming, let's say, HCO3 minus, if we're consuming that, then that was acting as a bit of a buffer. Even though I mentioned a minute ago, we produce a bit of H plus during photosynthesis, I think that the net effect, if you're taking away the CO2, there's a net increase in pH there. Okay, so if we look at that again and see, well, what happens when we like really see. This is actually, I think, fairly similar. I think this is just a different pond. The book didn't really explain the panels here particularly well. This is the one that becomes really interesting. I think that one was just showing, I don't know what. Okay, so this one is the particularly interesting one where we have a whole lot of algae growth, extreme photosynthesis, and we essentially consume pretty much all of the CO2. So we're up here at 10 times 10 to the minus fifth, so it's a much smaller amount, even with perhaps, well, up here maybe it's just a little bit smaller. But then we drop down to maybe 1 times 10 to the minus fifth, so a lot smaller than these other ones, which were 10 to the minus 2. Okay, so that's extreme photosynthesis, perhaps not enough CO2 added from the bacteria, perhaps poor mixing, and what ends up happening is our pH ends up skyrocketing up to about 10. That can be a problem if the bacteria that we want to have growing, maybe the algae are okay, but if the bacteria that we need are unhappy or are killed by that, then we may be in some trouble. Okay, so just kind of something to take into consideration for operators there. Probably not normally an issue, but there may be times where a little bit of shading may even be necessary. Okay, so thinking about what kind of solar conditions we have, we could take all sorts of estimations based on different calculations. Here's different latitudes, how much solar energy, and there's some unit here that I didn't copy in with the figure, but you can basically see if you're up, it's like looking at the min and max amount of solar energy you get at a given latitude. So if you're at the equator, pretty high numbers throughout the year, obviously. And then if you're up, 60 degrees latitude, which I think we're close to 30 here, right? So we're somewhere in this region. If you get way up north, you can see, like in December, if you're talking about the difference between there and the equator, it's 250 times different, right? It's quite a bit different. And then you'd want to account for cloud cover, which you can do with some other math and estimations. And then there's a few other factors. Again, more tables. The point is not to look at all the data necessarily, but just to get a concept of the types of considerations you would need to account for if you wanted to put one of these in Indonesia compared to sub-Saharan Africa, right? The cloud cover is probably very different between the two, even if maybe the latitude, distance from the equator, in some places, maybe that's similar, or maybe it's only a little different. Okay, so a few other factors here. So we've got that light energy and flux. That's kind of these pieces of information would go here. So given something like that, then we could consider, okay, well, what kind of detention period do we need in the pond given that amount of light? We can kind of consider the diurnal illumination, how much of the day is actually daytime versus nighttime, how much BOD we're actually adding, and the temperature. So all of these pieces would go into kind of giving you some guidelines on how to structure, how to design your system. Okay, and a lot of these are coming from our gas transfer reactions, our oxygen supply, essentially. So if we think about our oxygen supply, we talked about it, got the water temperature and the wind mixing, in addition to the algae. We already talked about algae. So here, if we wanted to estimate the effect of wind, we can do this in a few ways. Again, I'm not showing you the equations with the expectation of you learning them so much as expectation of you understanding what matters to calculate something like this, right? That's I'm wanting you to see the concept here. So this K2 is some constant that's defining how much oxygen we're getting given some conditions, right? So those conditions would be time, the saturation conditions for oxygen. So the equation here is -1 divided by time times the log of CS minus C. So that's going to be the saturation minus the current divided by saturation minus the initial. So for our initial concentration of oxygen coming into the lagoon, that would be this guy. Okay, so at any rate, we can get this constant that's telling us, okay, how much pressure essentially is being applied across the water interface. So that's just the Henry's law type of thing, right? That's how much is that oxygen being driven into solution based on the gas laws. Now, we would also want to combine that with some kind of empirical approach, because that's going to give us like probably just a still water, like what's happening at the equilibrium. That's not actually practical if you've got wind, which we are somewhat reliant on the wind for a bit of mixing and for that extra surface area, extra gas transfer. So people have developed empirical relationships to account for the wind and things like that. And so again, several equations here kind of dealing with kind of the amount of power that the wind is applying, what the wind speed is compared to then the speed of the flow that's maybe induced by the wind, and some other factors, the depth, and how deep is the water flowing. So if you've got a current that the wind causes by pushing across the pond, how deep does that current go? Like, is it just the first couple of feet on top of the water that's getting moved along, or is it enough wind that it's gotten a little bit deeper? So some factors like that are all sort of mixed in, and we can get some empirical derivation of that oxygenation rate constant that we're looking for as a function of depth and this oxygen transfer coefficient that accounts for the wind. Okay, so those are kind of the two factors that really go into it. And like I said, if you happen to be very curious, I'm happy to give you some more information about all this, but I'm going to leave it there for the moment. Okay, a little bit about the anaerobic processes. We have talked about it a bit already, but essentially most of the anaerobic microbes like a fairly neutral pH, pH 7-ish. So if we were to look at pH as a function of depth, we'll see that where the algae are growing and producing stuff, the pH is going to be a little bit basic. We saw that in the figures a minute ago. It should be 8 to 9-ish. But once we get down to the anoxic zone, we tend to have more reducing conditions because there's no oxygen, and that tends towards a bit more acidic, and that's good because the bacteria like that. So then it would probably be neutral, maybe acidic, maybe I'm wrong there, but more acidic than the photosynthesis region. Okay, so in particular, there's sulfur-reducing bacteria that are going to take, that are going to process our sulfur for us, essentially, and they are, so, okay, there's a couple things that are going to happen, right? It's going to be sulfur processing up in the aerobic areas, and there's sulfate down in the anaerobic that could be reduced going back to H2S. So essentially, bacteria are going to be doing one or the other based on where they are, right? And there's probably different species. So that's kind of all I'm pointing to is like the net result, what we want to happen in the upper area is we want to take that hydrogen sulfide and turn it into sulfur, and then take that sulfur and go get that to sulfate. Now, if that makes its way back down to the anaerobic areas, it's kind of going to be a reverse process, and they're going to be making use of that oxygen because they have no O2, and they'll kind of end up reversing that So there is a bit of cycling there that we would expect. One thing to note, however, so in terms of the, sorry, this is anaerobic and aerobic, I realize, so don't pay too much attention to that. So in the upper area, if we have too much hydrogen sulfide, it's not being converted quickly enough to sulfate, then we have an issue because algae will be killed if we have a hydrogen sulfide that reaches about 6 milligrams per liter. So hydrogen sulfide is not too friendly to the algae. It's actually quite poisonous, and we are very, very sensitive to it smell-wise because it's so toxic to us that we smell it way, way, way before it's at all toxic. So that's the good thing, right? We will smell it at a very low concentration. It seems like that's a evolutionary trait. Anything that's starting to rot, we should probably not eat, so we're very repulsed by it. Okay, anyway. So then typical variation would be nearly 0 milligrams per liter during the day for hydrogen sulfide, and maybe 1 to 2 milligrams per liter at night. So if we have some maybe sulfur-rich influent coming in, maybe that can become a problem, or if we have perhaps very, very cloudy days, several in a row where we're really not getting much of the oxidation occurring, maybe that could be a problem, or something with winter. So one consideration, the algae can all die off or disappear, I guess, for a time if we have too much hydrogen sulfide. Okay, so in summary, we have this little picture from our book. We've got gas exchange, CO2 and oxygen, both important. That's going to drive our primary biological processes up at the aerobic zone. So it's good if we have a bit of wind. If we have really stagnant conditions, airflow-wise, we might have some issues with not enough aeration. Algae are going to provide some aeration, so there's some hope, even if that's the case, especially with lots of sunlight. There's going to be kind of counteracting forces here with CO2, oxygen, and where the mass is going. Ultimately, we're getting lots of cells formed and dropping down through the anoxic zone, where some things will dissolve and into that anaerobic that's purely no oxygen, and sediment down there accumulate and be digested, right? So it's constantly growing microbes, they're constantly dying and falling, and it's kind of cycling slowly through that process. And we have different biochemistry in each spot, and ultimately the combination of all this gives us a few different approaches to process the wastewater, and we end up getting a decent amount of pathogen removal in the process. The sunlight itself is going to cause lots of photoreactions, photochemical reactions, even the heat from that, or from the sunlight. All those factors together will provide slow, kind of mild disinfection, especially when we have other microorganisms that are out competing, happier to live in this condition. Probably going to have predator microbes, like little amoebas and things, that will be scavenging stuff. So we end up with a bit of, I think I have a slide on it, but we end up with a little bit of pathogen removal, which is always a good thing, and actually a pretty good waste removal in terms of BOD nutrients. Okay, couple notes on the types of plants and bacteria that can grow or should grow in the systems. We had a question about that earlier, like, can you plant stuff around it that's intentional? Well, actually, there's some plants that might grow inside the treatment system, and if they can, that's usually not too much of a problem. In fact, there are some ponds that are designed to use hyacinths. So rather than use algae, you can use a plant like that, and there is maybe some consideration because they're shading a lot. Maybe that just creates a larger anaerobic zone, or that might change the zones a bit, but it's certainly something that could be used in place of algae. So it'd be some sort of surface cover plant. So we've got some green plants. Essentially, the source of, we could take a look at their kind of what they're useful for, or what they require, right? So the source of reducing power for the green plants, hydrogen sulfide, got green bacteria. They could be useful for the hydrogen sulfide and make use of other inorganics. Purple bacteria. We've got, so those kind of are the three categories that are common in a wastewater treatment lagoon. So can they photosynthesize oxygen? Okay, green plants, yes. Bacteria, no. And then they're getting their carbon. Generally, most of these are from CO2 or from other organic compounds. Okay, and then the relation to oxygen. So plants obviously have to be aerobic. Green bacteria apparently are anaerobic. And then these purple bacteria can be strictly anaerobic or that facultative zone. Okay, so that's just kind of some of the common things that you would see. Okay, so how about in application? So if we're going to go ahead and design something and install something, you know, here's would be a kind of a small lagoon setup. Well, we have to consider what kind of flow rate we need and what kind of wastewater strength we have. If we put something in here where we flush like 20 times a day or more, just whatever we feel like, and we use a lot of water compared to the amount of waste we have, that we might have a lot different wastewater strength than somebody who's using half a bucket for flushing solids and not really flushing if it's just liquids, right? So that would make there'd be a much stronger wastewater strength in the latter case. So if you've got a condition where there's not a lot of access to water, but you do have flushing systems discharging the wastewater, then just that could dramatically change your wastewater strength, right? So there's some considerations here in terms of that organic loading, how much BOD per day do you have, and what does that look like in terms of the flow rate of water itself. So you might have small flow rate, but high strength. Okay, so there's some calculations we could do just to calculate, okay, the grams of BOD per cubic meter per day, and we could relate that to the lagoon volume, right? So that's maybe a kind of the easy way to estimate what lagoon volume you need according to maybe some lookup tables. So if we're using, let's say, an anaerobic lagoon, we could take a look at these organic loading rates. If we have a loading rate of somewhere between 100 and 350 grams of BOD per cubic meter, then this one is acceptable. The facultative lagoon, and remember, this is that anaerobic one that was high strength, right? So perhaps if we have that condition where we have a high waste to water ratio, maybe we have to do an anaerobic system. All just depends a bit. Whereas a facultative lagoon, that's in the 15 to 80 range, whereas that anaerobic is 100 plus. Okay, so then that kind of guides your water depth. Then you have to design your hydraulic detention time. So for an anaerobic system, you need 20 to 50 days is kind of what you target. It says a minimum of 1 day, and that'll give you 60 to 70% removal, kind of temperature dependent. It's going to remove Vibrio cholera and helminth eggs. You're not going to be able to survive that process. Some other viruses, bacteria, are probably still going to be there. So you're not necessarily going to remove everything, but either way, Vibrio and helminth eggs tend to die off. So that's a good thing. For the facultative lagoon, you really need a minimum 4 days of retention time, but you ideally have 20 to 180. So if you think about that 180, that kind of draws me back to viewing that Michigan site where half the year, the winter and still winter, you're essentially frozen and can't really do anything. So you've got a residence time there that's very large, and they have to design for that to hold the water and then allow treatment once it's warmed up enough before discharge. Okay, so a few things about removal efficiency. If we look here, we've got BOD, and this is for facultative lagoons in series. So if you've got, kind of like those pictures showing, you have a couple of lagoons in series, you go from one to the next. You've got BOD somewhere between 70 and 95%, so pretty good removal. Total suspended solids here, TSS. Would also be pretty good. Again, it's basically one long sedimentation system, right? So aside from the whatever suspended solids the bacteria are, keeping suspended, and whatever might get kicked up from the wind, you're going to usually have pretty good removal. Viruses, somewhere between 2 and 4 logs. So somewhere, 99% of the viruses. Well, if you had a lot of viruses to begin with, that's, maybe still a big hazard. But certainly not too bad. Bacteria tend to be, again, 2 to 6 logs, depending on what it is. Again, could still be a hazard, but cholera, for example, does a pretty good job killing that or mitigating it. Helminth eggs, we don't typically find these eggs at the same concentration, so you're not expecting millions and millions of helminth eggs per liter or whatever, like you might bacteria or viruses. So the 2 to 4 logs, that's probably a bit more meaningful, meaning we've got pretty good treatment in that sense. And protozoan cysts, also decent. In part because some of these are probably going to sediment over time. There's a few different mechanisms. I mentioned like the photochemical stressors. You also have adsorption to other particles, sedimentation, all of that. So there's a few ways that we get some mitigation of pathogens. All right. One nice thing about treatment lagoons is you can just kind of look at them to see if they're going wrong. You use your eyes and use your nose, right? If you smell something rotten, you know that it's not getting enough oxygen, which may mean the algae are in trouble, or it may mean it's just really not windy enough and could really do with a bit of mixing or something. And maybe if it just goes anoxic once a month or something, maybe that's okay. If you can do something about it, or if it's happening for a longer time, you realize you have to do something about it. But ideally, it's going to be a bright, rich green. So that indicates that it's good conditions, plenty of green algae. Green color is suspended throughout the water column. So you want it to look green and toxic looking, vibrant green, because that means there's lots of algae, it means there's lots of photosynthesis, it means there's lots of biological activity. So a dull green or kind of a yellowish color, maybe there's a bad algae growing, some sort of filamentous algae, which can be a problem because you're going to end up creating a film, which is going to limit gas transfer, right? So that, if you get the wrong stuff growing, it can be a problem. So blue-green algae are stringy and can clump, block sunlight, cause hydraulic short-circuiting, and they may exhibit a green pea soup color. They dominate lagoons when the pH is low or when protozoa eat all the green algae. So you can have random ecological disasters just based on the wrong protozoa getting in there and ramping up and populating. So an interesting, to me, a research project that I've proposed before, even though I'm not quite an expert, we haven't gotten any money for it yet, but it's just kind of an idea, is if we have lagoons like these, or like the one in Mandeville, discharging to something like Lake Pontchartrain, well, these algae have some defense mechanisms, the cyanobacteria. And the harmful algal blooms are essentially that defense mechanism triggering in mass. And so that defense mechanism is to produce some sort of toxin, right? So the conditions in, let's say, a wastewater treatment lagoon may, and I don't know if this is true or not, may have some impact downstream for algal blooms, right? Because these are the types of ecological competitions that are happening naturally. So something that I'm curious about, don't know enough about yet, and might one day get to research something like that. Okay, gray or black, if that's what your stuff looks like, you really don't have any photosynthesis happening. The green color is very indicative of that because the molecules that absorb light, all that. So that means you're really anaerobic. Tan, brown, or red, you might want to take a look at your soil conditions, seeing if you're eroding soils into it. Maybe there is some flooding. Possibly there's some other different algae. And you would probably know, if you had a system and you were the operator, you'd kind of get a feel for what your typical biology looks like. Your pond normally looks like this, and then suddenly see a difference that you're going to be thinking about that. Okay, we'll wrap up with this. So at minimum, routine maintenance should include the following. So you'd want to take care of the grit removal, the screen. You don't want stuff going out and clogging. Periodically cutting the grass. We mentioned this to prevent burrowing animals and remove vines or other plants that could harm the liner or the soil. You want to remove scum, unwanted algae types, floating plants, assuming you're not going for the floating plant type, because you want that light to happen properly. You want to take a look at the inlets and outlets to make sure they're not blocked. Standard kind of stuff that you can do once a week, or maybe be on site a few days in the week, check things, maybe a day of maintenance per week or something like that, remove sludge from the lagoon every year, or at minimum every 2 to 5 years, when the lagoon is 1/3 full of sludge. So like our septic systems, that sludge will accumulate. There's some maintenance required in removing it. Kind of depends on the operation. Sometimes you might try to design, like it says, designed to store sludge over the design of their life, but you're going to require, probably require every 5 to 10 years, if not what they were recommending here. Okay, so with that, I'll let you go. Thanks again for your patience at the start of class, and good luck for all your senior design competitors.
Thank you.
And for you all, we'll see you in a couple weeks, but most of you see you Monday.
Yeah, that was